So we have the pleasure to have with us Professor Juan Fuster, who is going to give us an update on the progress, the status, and prospects for, of the Linear Collider. So,
thank you, Masron. Thank you for the organizers to invite me to report on the activities on the Linear Collider and the perspectives that we have in the close future. We don't know whether long future, but at least close future. Okay, so the outline of my talk is I will introduce a bit the situation on the future colliders, the status of the International Linear Collider, the ILC. Then I will go through the physics case for E plus E minus linear colliders, and then the summary and conclusions. Oops. No va? Yeah. Pero parece. Okay. So first, let me show you what is the landscape that we have for colliders. So we have essentially two main columns, which are the hadron or proton colliders, and then the lepton colliders. Yeah? So for the proton colliders, we know very well that LAC is now in operation, in run, and has still a long program to be realized. So we have already collected almost 150 inverse femtobars. You know, then we have now a shutdown for a couple of years, and then it will start again in 2021. Then we will start for a few years more, and then there will be what is in 2025. There will be the process for the high luminosity, which will last then up to 2035. That's the proposed. In there, also for the future, as they have been proposed, two different colliders have been proposed. The one which is called the Future Circular Collider Hadron Machine, which could run at 100 TeV, and the high energy LAC, which would run at 20 in the 30s TeV. It's not clear exactly, but 25 to 30. So the FCC would need a new tunnel, about 100 kilometers tunnel, whereas the high energy LAC would use the same tunnel as the LAC. So on the lepton collider column, we have the linear colliders and the circular colliders. So for the linear collider, we have ILC, which already is quite mature. It has a technical design report, which was already produced 5 years ago, and now has been a process exactly, I mean, to demonstrate its possible realization. Then we have CLIC, which is, well, ILC, as you know, is proposed to be hosted in Japan, and the CLIC, which is the proposal for a linear collider at CERN, in which there is a conceptual design report. The ILC could run from 250 to 1 TeV, essentially, and the CLIC is expected to also enter into the multi-TeV region of up to 3 TeV. Then on circular E plus E minus colliders, we have today two proposals. Which one is in China, which is called the CEPC, that could run from 90 to 250 GeV up to the Higgs threshold. And then also in combination or complementarity with the Hadron FCC, using the same tunnel, it will be the FCC running as an E plus E minus machine. That would cover the energy region from 240 to 350. And then we have also the flavor physics, which are running nowadays, and Bell 2 has already started. I put here seen in operation because it's sorry for that. And then also to this column, I said it is lepton colliders because there is a renewal interest now in also developing muon colliders. So that is also something. So first of all, you know, one of the things I would like also to point out is the importance of polarization. So, and E plus E minus, as you may know, I mean, we have been working on LEP, then LAC, And here you see essentially which are the parameters that are used in our electroweak fields, which are sustaining experimentally the standard model. And here you see where they come from and where there are the most precise measurements, which are the basis of the standard model. So you see that even though E plus E minus colliders are not running since quite some time, they are still in most of these experimental values which are giving the standard model the power it has, okay? And furthermore, you see this SLD, and SLD, I remind you that it has something like at least 10 less statistics than LEP, and it still was more competitive for certain measurements for the standard model than LEP. And that was thanks to the fact that they could use polarized beams. So E plus E minus are still the basis, or are very important for the standard model, and polarization is important. So the International Linear Collider, just to understand our feeling, how we feel, let me introduce this sentence of the old classics. So they buried it as Spartan because although he was one leg, he was going to a battle. And he responded that his purpose was to fight, not to flee. So as you see, our project is there for more than 20 years, and that is a real battle that we have still in there. So how we are organized? So there is, we have, as it is not on the ILC, there is not a, today, or there has not been a lab which has been proposed as being the host lab. We have organized, we have a worldwide organization. Okay, this worldwide organization is called the Linear Collider Collaboration. So it is under the body which is called ICFA, which is the International Committee for Future Accelerators. So Jeff Taylor from Australia is the chair of it. Then there is the Linear Collider Board, whose chair is Tatsuya Nakada. And then there is the, somehow the executive body of the Linear Collider Collaborations, in which the director is Lynn Evans, deputy is Hitoshi Murayama, and then there are 3 boxes in which the different projects hold on, which are the ILC for the machine, whose director is Shin Mishizono from Keck, then on CLIC, then is Steiner Stabnes, and for physics and detector, Jim Brown from Oregon. So the main milestones for the ILC were first in 2004 was to decide which was the technology to make the accelerator, which was the superconducting RF. Okay, and then in 2013, it was as I said before, the technical design report, which means that from then on, all technical major issues were resolved and no major stoppers were expected. So of course you always have to develop such big projects, but that already guarantees that the project could be realized and constructed. So this is the collaboration. Essentially, it's a snapshot of the collaboration and all the countries which are involved. Then here are the main parameters of the machine, of the accelerator. So in principle, you know, the ILC TDR, that as it is in TDR, so it can run to 200 to 500 GeV with a length of 31 kilometers, and it could reach up to 1 TeV, which with the present technology would reach 50 kilometers. Then the beam size, this is a high technological issue, which is to reach 6 nanometers beam size. Okay, and the luminosity, which is expected, is 2 times 10 to the 34, and could be doubled. And polarization, they can run. ILC can run with polarized beams using electrons at 80% and positrons at 30 or 40%. So, and the main advantages of linear collider is that there is no energy loss due to synchrotron radiation. It can be extended in length and in energy, polarization, and allows also for energy scanning. So these are very important and significant features that only linear colliders have. So also proving that how mature is the technology. I mean, since there are already many machines operating worldwide and using this technology. An example of that is the X-FEL at DAISY. And that also what means is that there is already an industry which knows how to deal with the important pieces of the accelerator, mainly the superconducting RF cavities. So it has been proven that all these places can build these cavities and according to the specifications required for the ILC. So therefore, all these are prepared and have demonstrated that they can be industrialized. So the place which is proposed is in the north of Japan, in the area which is called Kitagami, and it is the area which suffered this tsunami a few years ago. Oops. So since 2013, as I told you, there was the TDR, the technical design report. In this TDR, the proposed machine was to start at 500 GB. However, the cost was seen also as relatively high. And what was proposed was to, thanks to the fact of the extendability of the machine, what it was proposed was to start as an earlier stage with a lower energy. And this lower energy would allow to make mainly Higgs physics at 250 GB and then reduce the size and the cost of the accelerator. In fact, there are several scenarios which I think there is not a firm decision on which scenario to run, but maybe you cannot see here. Okay, but they represent something like a 40% reduction in the cost and leaving the accelerator that could be extended to the highest energies later on. The process in Japan is also quite mature, and we are expecting that Japan should take a decision. It was expected to be taken this year already, but as you see, we are already in December. ¿Lo he pagado yo? Sorry. This is because I didn't want you to know that. Okay, so as you see, it has reached already the highest level on the Japanese government. So this is the Prime Minister of Japan, Mr. Abe. And it's really being seriously considered by the Japanese government at this moment. So what about the physics? You know, here I always like to say that, you know, essentially the two projects which are for linear collider, ILC and CLIC, have essentially the same reach in physics. And, you know, it's not the end. It's more a question of what is the highest energy they can reach, but also that depends on future developments. You know, if we have a project like that, 15, 20 years, so then there is a lot of development and research. So what we are thinking now is unthinkable. We cannot be reached. Maybe in 10 years or 15 years it can be reached. So I think that reaching 1 TB, 2 TBs or 3 TBs within reach for both. But also another issue to be considered is the technical readiness of the projects, in which I believe that ILC in this sense is more prepared than CLIC, but still is a possibility. So for many years we had the top quark, which has been in collider physics, you know, the star, and the one which really was giving us the highest, you know, was the star of the particle physics world. But now, since the Higgs has been discovered, it has taken the power. So then essentially the main role of is concentrated on the Higgs. So here is a slide in which you can here see the different production modes of to see the Higgs process, in which the Higgs process can be studied and produced in E+ E- colliders. And there you can see here the reach of each of these colliders and the different processes which open as you run up with energy, right? So we should start something like here and there, and then we would really have access to measurements of the Higgs parameters in a model-independent way with a very high precision. And then in later stages, we could open to other processes, for the top threshold with associated production with TTH, and also the triple Higgs. Okay, so what about the precisions which could be reached? So essentially, you see that we can, in this cell, we can measure cross sections of Higgs with a percent precision, and we also have the width with 20-30 MeV precision. So one thing, as we believe that it is also complementing all these measurements that will be reached by the program of the high luminosity LHC, is that it provides, first of all, a higher precision, and second, a model-independent test. As you know, in LHC, you have to assume the standard model really to measure the properties of the Higgs. So that in E+ E-, you get released from this condition, and there you can really make model-independent tests. Okay, so that and here these plots are not updated now, since we are involved on the strategy process for Europe. Then all these plots are being now reproduced by the collaborations in LHC, also by the E+ E- colliders. But essentially, I think that the main message remains. So the numbers are not correct, because now all the prospects is that everybody will do better than what is expected there. But at least what you can expect is that the linear collider will improve the LHC measurements by a factor between 5 and 10. And what is more important, it will reach the sub-percent precision, which is also essential to test many models. Okay, so again, here, one of the important things to check also is the Yukawa coupling. So, when you really plot all this mass with respect to the Yukawa couplings with the Higgs, and you should expect a straight line. And any deviation from this straight line should imply new physics. So that, of course, depends on how precise you are. We already know that at LHC, nothing from direct searches, nothing new has been seen. That implies already that any deviation from a straight line is not expected to be very high. So if there is a deviation, it can only be seen if you have a percent precision. Otherwise, you are not really testing something that you don't know already now. So on the triple Higgs, I go fast, but what we expect is to have a precision which will be at the level of 10%. It's quite difficult. I am sure that we will improve having better methods, but today we can ensure that at least a 10% precision will be reached. Okay, as I said, what are also on the 250 machine, what are our prospects? As you know, also there have been developed now this new type of understanding the standard model, which is the EFT effective theory, and in there you can get a bit more information on your fits. You would make a global fit on that, and that is more updated plot than what I showed in the previous one. And then what is important is that again, it reinforces the high precision on the Higgs couplings, then also the high capability to distinguish among the different models, the standard model and beyond the standard model. I mean, if you have other models, you want to really be sure that the others are not fulfilled, and you can want it. And furthermore, again, one issue is that to get this high precision polarization is important. So here you have some plots in which in green or red means it is a comparison to which type of models you would have distinction. 5 minutes, okay. So this, we should not forget also that there were things left by LEP, and they are there because we have not reached higher precisions, and I think you may remember certain asymmetries on the bisector and this in which they are at the level of 3 sigmas, and maybe these are things which the E plus E minus or the ILC will measure with higher precision now. So the top quark, I'll go fast, but okay, then we can produce top quarks at the top threshold. And again, you know, here is, you can see, I mean, you want to distinguish different models in new physics, anomalous couplings. So this big ellipse tells you what should be what you will reach at LAC, and this small point here is what you will reach for these models within this kind of space for the ILC. Again, also on the top mass, I think the top mass is a very important parameter. As you know, it has many implications in many aspects on the stability of the vacuum, etc. So in E plus E minus, first, the way to measure the top mass is well defined, and second, the accuracy that you can reach is at the level of 30 to 50 MeV. So it's really a huge improvement. Here also, here you also see a comparison of how the anomalous couplings measurements improve with respect to the LAC, and this scale is logarithmic scale, so that means that in some instances you get even 100 better than LAC. Okay? That is also the group of Valencia is very much involved in making this type of analysis. Okay, so here the top and the Higgs at the end are get friends, you know, these things. You will never have enemies forever or friends forever. And of course, you have the Higgs, which is the particle given the mass to the elementary particles, and you have the top, which is the particle which has the heaviest mass. So certainly, if we want to find something which is not behaving as we expect from the standard model, this is one of the places really to look for, because you have the two main actors of the mass. So what is the reach for the ILC? Okay, so at the first stage, we could go to 6 to 4%, and finally we could reach a level of 2% accuracy on this measurement. Okay. On the new physics, as I explained, the main thing is the ability to distinguish and to distinguish models in different couplings, and there the main thing is to really have a precision which is at the level of 1%, because the models themselves differ very little. Okay, so what is more than 10% has already been discarded at LAC. We know that does not exist. How can complement ILC and LAC? There are still maybe corners in LAC for direct searches, which have not been investigated correctly. You have, you know, you have degeneracy, and then places on the phase space which you didn't have the ability at LAC, and there with a linear collider you can reach. And there is a clear example. You see that at the Tevatron, more than 20,000 Higgs were produced, more than 20,000. But Tevatron never saw the Higgs. So don't be scared. There are things at LAC that are maybe escaping LAC. Okay? And okay, polarization here is an example. You see here a search, for for its muons, and then you see whether, if you don't use polarization, the signal is relatively difficult to see, whereas if you use it, then the signal really appears very clearly against the background. Okay, so then if you include higher energies, about 1 TeV, then also there are many more processes which will open. On the dark matter, okay, I think that the main strategy in E+, E- is to look for WIMPs, right? And the way is to look for single photons in which the dark matter candidate is not seen in the detector, and then what you see is a single photon. Here again, you see here is the accuracy and somehow the reach that you can get for this dark matter WIMPs search. And again, you see that while using polarization or not using polarization is essential, and you really have a big improvement. So summary, the linear collider collaboration is working, is in a structure worldwide, and because of this 250 GeV proposal, there is a new scenario, okay, which makes the project affordable, or more affordable, and that really has opened the possibility to build it in Japan, and that implies a 40% reduction from what was proposed originally at the TDR. So that has been well received by the physics community and also by the politicians, and both in Japan and outside Japan. The ILC 250 can provide these model-independent measurements, but also make important contributions to searches. This committee for future accelerators has also reacted very positively to this plan and to this project to start with this 250 GeV. So I think that the rest of this year and next year are crucial for the project, and I believe that there will be a decision, and no decision will be a decision. Okay. And okay, so in Europe, as you know, we are now very much involved in preparing our strategy for the next 4 or 5 years, and essentially what will happen. And any statement, as I said before, from the Japanese government will be welcome and will have a big impact, I think, in the discussions. We expect that the Japanese government will make a statement, positive or negative, before the 7th of March next year. Okay, so, that's my personal thing. You know, as I said, for many years we have been working on this project. We have been promised many times that maybe ILC will be next year, or next year there will be a decision, or next month. And you see here this scale that it was up to now, all them were illusions. and that makes us being a bit skeptical, okay, but who knows? You know, maybe this time we don't believe it can become real, and it is real. So thank you very much.
Are there any questions to Juan? Even aggressive questions are allowed.
Cannot be more aggressive than what we
Okay.
have.
Can I?
We all know all the aggressive questions.
How can you improve on sine squared theta weak through this polarization?
I don't know. That is a very, I don't know that.
That's one basic parameter, weak parameter.
Yeah, but this I don't know. This I believe this is more on the gigaset, what you can improve there. So not at 250, but at 90 GeV, right? And there you would need something like 100 more luminosity than what was produced by LED. And this is certainly in the program of the Chinese machine, the CEPC. not clear it is in the program of FCC, and in the program of ILC is difficult, because technically going down in energy, you can do it, but it is optimized to go up. Okay, so ILC, I don't think will be a machine making a step on that.
It's more
A circular machine from those proposed, I think will do.
Yes, please.
We know LHCb is seeing a kind of violation of lepton universality. So if this signal is becomes real, do you think it's better to build a lepton collider or continue at the energy frontier?
Well, one has to understand if that is real, which are the processes which can be investigated, and then is when you find from these processes which is the best machine. Okay, if I think that LHCb is seeing all these things through a scale for from radiative corrections. So I don't know what the scale implies. I don't know which is the scale implied.
Something below few PeV.
Below?
Few PeV.
Then I mean, if we can make a machine on E plus E minus which reaches this scale, which is 1 TeV or 2 TeV, it's something that can be produced, and that's why we have to keep all that. If not, then we have to see.
I think it's an interesting question. Any new physics at a scale below 10 TeV is good news for any future collider at this point. We really need some motivation to go there. And to know which machine is best, we really have to know where it is. And that is the problem with the failure anomalies.
In any case, you know that if you get closer in energy, yeah, I mean, if you go above the scale, you can produce these new particles or what is implied by these new phenomena. If it is below, the closest you get to the threshold, you get then more effects or a higher effect. So, but one has to really go into the detail of how these processes are produced and what are the implications for an E plus E minus machine.
You need to know what you're looking for.
Well, yeah, or at least to have a hint. Okay.
Okay, so one last short question.
You were provoking.
It worked.
So it's a naive question. All those cavities of the electric field go through. I wonder, what can we expect in the future in terms of improvement?
It's a very important, and that is one of the key questions. This is very important question. Is one of the key questions. So today, what is being reached and what is being ensured that we can industrialize is 31 to 35 megavolts per meter. Essentially, the technology, at least the experts on the technology say that the reach of the technology could be up to 50 or 60 improvement. Maybe this is a limitation on the technology, but probably something like 40 or 50 is in reach. So that means that even that if we could start today to propose building the linear collider, maybe in 10 years, with the same price, because that is important also, the price which is attached to this technology, with the same price, then we can already have a machine which maybe is not reaching 500, but is probably reaching the top threshold. So what we are proposing today to be 250 machine, in 4 or 5 years, could be reaching also the top threshold, and then we can also make the top physics already at the earliest stage. Okay. And then if you have a full program of for 20 years of development, one would expect that even other technologies can can come. There are people who are thinking that an upgrade of the ILC could be click, because click can go up to 100. No, it's a very important question.
Okay, thank you, Juan, and thanks for the questions. So we now move to the next speaker, to Dr. Juyun Ding, who is going to discuss the origin of flavor mixing from dihedral groups and Dirac neutrino masses. Please.
So, firstly, I thank the organizer for invitation. I slightly changed the title. In this talk, I will discuss the possible new physics in both flavor mixing and the Dirac neutrino mass generations. So, firstly, we go to the flavor mixing. And if you well know, quark mixing and the Lambda mixing are very different. The quark mixing angle is small, and the largest one is the Campbell mixing angle between the first generation and the second generation. But for the Lambda mixing, the C1, 2, and C2, 3 is larger, close to 45 degrees. And the C1, 3, the reactor mixing angle is about Campbell mixing angle over √2. It will same order. For the CP violation phases, the angle R of the unitary triangle, secant unitary triangle, is around, it is about 18.8 degrees, about 90 degrees. For the Lambda sectors, the Dirac CP violation phases have been not measured precisely, but we have indication from both departments such as T2K, NOAA, and the global analysis, and it is close to 1.5 pi, around 1.5 pi, for both normal hierarchy and inverted hierarchies. So this is around about 90 degrees, and this is about minus 90 degrees. This is the situation. So in the past, many people have been trying to understanding the quark and Lambda mixing from flavor symmetry and CP symmetry. And the basic idea is this: we assume there are flavor symmetry and CP symmetry acting on the 3 generations of fermions. They link different generation fermions, and the flavor and CP symmetry have to be spontaneous breaking down to different subgroups in the child lambda sector and the neutrino sector. Similarly for the quark sector, similarly for the quark mixing. And the lambda mixing arises from a mismatch between radio symmetries. So this is the basic ideas. So there are a lot of flavor symmetry groups have been discussed. Here I list some smaller discrete groups used for model buildings, listed by Adrali and Frugli in his review papers. And but usually, especially after C1-3 was discovered, usually the 3 generations of lambda leptons are assigned to irreducible and feasible 3-dimensional representations of the flavor symmetry group GF. So usually, so the flavor symmetry group generally is required to have a triplet representation. The minimum one is A4, and S4, A5. But the CP symmetry changes the situation. It's not necessary. Then we revisit the simple group, dihedral group DN. It is the simple one. You can see the simplest one, the DN. For the DN, the dihedral group DN, it is a symmetry group of n-sided regular polygon. So it has 2 generators, R and S. R is a rotation around its symmetry axis. So nth power of R is 1. S is a reflection. So around the axis to refraction. So its order is 2. S square is unit. And their product, RS, is also order 2. So the group structure is very simple. For the representations, they only have 1-dimensional representation and 2-dimensional representations. So they have no triplet irreducible representations. If n is even, there are 2 additional signals, 1-4 and 1-3 and 1-4. For the 2-dimensional representations, it is just the rotation around its symmetry axis. So it has such representation. Both representation matrices is very simple. So this group is just rotation or reflection around certain symmetry axis. Now we combine the CP with the DN. So this has been discussed by mutual chain comparison. So I just give the final results. Here the CP transformation is called the general CP transformation. That means they map a field multiplet into its complex conjugate. It is for a scalar. For Fermi field, it's the same. It is similar. But the CP transformation X, it is generally unitary matrix. It's not required to be diagonal. If we want to combine the CP and the Fourier symmetry consistently, the symmetry have to be well defined. That means it have to be closed. We first perform CP transformation, they become phi star. Then we perform a Fourier symmetry transformation, there's still star. In the end, we perform the inverse CP. So in the third step, the star, the complex will be disappears. So equivalently, if the symmetry symmetry is well defined, after these three steps, they have to be equivalent to another symmetry, Fourier symmetry transformations. So this is the meaning of consensus condition. So Fourier CP symmetry times the Fourier symmetry conjugate of Fourier symmetry times the inverse CP, they have to be another Fourier symmetry transformation G prime. G and G prime may be different. So the CP transformation map one element G into another element G prime. It is automorphism. And it has been proved by Muchun and his collaborator. This transformation, this automorphism have to be class inversion automorphism. That means the G prime and G inverse have to belong to the same classes. So we solve this consistent condition for the D in this basis. We find the CP transformation and the Fourier symmetry transformation is the same form. So this looks like a good basis. Then we come to our games. How we predict understanding Fourier mixing from Fourier symmetry and CP symmetry. We give a universal. Our aim is to find a universal Fourier symmetry for both lepton and quarks. So generally, we start from a Fourier symmetry and consistent CP, and then they are broken down to different subgroups in the general paradigm. So in our scheme, it is both charge sector and neutral sector in the radial symmetry group is Z2 times CP. So for give the radial symmetry, it completely fixes the neutrino fixed mass matrix and its diagonal linear mass matrix. For these cases, we only need to perform a Takagi federation for the CP transformation. XL, it is equal to unitary matrix times its transverse. And this sigma L is the Takagi federation matrix. You have to be satisfy this condition. You have to diagonalize the radial Fourier symmetry because it is Z2, so it is plus 1 minus 1. And similarly for the neutral sector. So the radial symmetry only constrains the mixing matrix up to a free parameter, Z2 times CP. This is the power. It has no constraint on mass completely. Then we combine the mismatch. We combine the charge sector and neutral sector together. We got a master formula for the mixing matrix. So up to row and column permutation because we cannot predict mass in the schemes. So there are two parameters, C, L, C, and U, three parameters. All the mixed angle for the left sector, three mixed angle, the three CP vector faces from around neutrinos are predicted in two free parameters. So it is very predictive. And it only relied on the symmetry breaking chains. And how we realize this symmetry breaking, how we realize this radial symmetry by introducing some Flavin fields or some other mechanism is not irrelevant. So it is completely fixed by symmetry. And this scheme is a universal scheme. So we can extend this scheme to the quark sector. We just replace the child lepton to the up quark sector and the neutrino sector to the down quark sectors. So the same master formula applied. That means for quark sector, we have two parameters to fit for three quark mixed angle and one quark CP faces. It's not easy. But we find the complex CK mixing matrix, both mixed angle and CP faces, can produce from simple dihedral group DN and CP. And we firstly, we assign 3 generation of lambda quark field into 1 plus 2. There are no triplet repetition. The first generation is a one-dimensional, and the second, second and third generation is doublet repetitions. Then we choose the radial symmetry. The Fourier mixing is completely fixed by symmetry, and it is E2 generator is S times S in reflection times the rotation, the power of x index 0 to n minus 1. And this is the CP transformation for up quark sector as Rn over 2's power. So n have to be even in these cases. And this is the down quark sector symmetry. Then we use the master formula to extract the mixing matrix into this one. And the one element is fixed, the 1, 2 element. CT is the capable mixing. The cosine phi 1. Phi 1 is a discrete parameter determined by radial symmetry, determined by this index x or y. You can choose as you want. And so we have 2 parameters, CTU, CTD, to explain all the 4 parameters. And we 2 parameters to explain 4, so we have 2 predictions. And this is the sum rule of called product rule favored by cosine. So first one is this one, is the capillary mixed angle cosine C 1 3 square times sin C 1 2 square into cosine square phi 1. The second one is we related the mixed angle, quark mixed angle with the quark CP Wheaton physics. So we input this parameter value of C1 3 and C2 3, we can get the CP violation physics, CP violation Yasko invariant or quark sectors. And we choose phi 1 equals 3 pi over 2 over 7. So the group is n equals 2, n equals 14, d14. It's order, it have 28 group element. So we can choose n equal to 14 and y minus x is 6. Then we can find two values for the free parameter CTU and CD. Then both mixed angle and the CP phases Yasko invariant can be described very well. I think before the CP, we just can explain the capillary mixed angles without fine tuning. But in this case, we can predict the CP physics. For Laplace sector, it is same as Z2 times CP, so it looks like no different. The symmetry is different. The symmetry is structural symmetry is same, both Z2 times CP, but different discrete parameters. That means different radial symmetry. The x, y is different. We choose it is 2 pi over 7. It can be realized. Then this is the mixing matrix. It is still 2 parameters. And directly we can get one sum rule. It's related C13 and C23. It's cosine square, product of cosine square is cosine 2 pi over 7 squares. And the currently can be fitted very well. 2 parameters input 2 parameter values, we can get the chi square is about 1.8. And the C23 is close to the present best fit value, 0.6, and the third CP is around 1.5 pi. We also have predictions for Majorana phases. Furthermore, this prediction is very predictive. You can see the allowed regional parameter space is very, very small. You can hardly see. It is in a tiny spaces. Only this black arrows. So it is very, very predictive. Besides this game, we have other approach to play this game, with the Fourier symmetry and the CP symmetry in DN. Then we give another scheme to play this game. This game is we choose different radial symmetry. So the idea is same. The general approach is same. So the different is we choose different radial symmetry, different symmetry breaking chains. In the challenge sector, it is a billion subgroup. Zn or the product of Zn. So they can distinguish different three generations of leptons. In the neutrino sector, the only a single radial CP symmetry. So for the tandem sector, the mixing is completely fixed by radial symmetry, and it diagonalized the radial Fourier symmetry GL. GL is the rotation matrix of Fourier symmetry group. For the neutrino sector, we still perform Takagi factorization. That means x nu equal to sigma nu transpose. Sigma nu is a unitary transformation, and this is a u nu. But in these cases, one CP transformation only fits u nu up to an arbitrary real orthogonal matrix, or 3 by 3. It is parameterized by 3 rotation angles, say 1, 2, 3. So finally, in this case, the PMS matrix is this form. It predicts up to a free real orthogonal matrix, or 3 by 3. So it has only 3 parameters. Firstly, it is 2 free parameters. Now it is 3 parameters. Similarly, we can extend this scheme to the quark sector. And we scanning our possibility. We find the minimal symmetry, minimal small group is D7. So it is a symmetry group of 7-sided polygon. It is very simple. Its order is 14. I shall not give concrete examples because of time. So I think this is rather. I think this is. I guess this is smallest thing. It should be hidden some. Maybe we can learn something from this case. In addition, Dean can give others more things to explain the lepton mixing. Firstly, we can get the mutual refraction widely discussed in the literatures. The idea is very simple. So the mutual refraction is a single radial symmetry. So we choose the GL is RK, K's power R. R is diagonal, and S is refraction. There are no 3-dimensional representation, so X is direct sum. This is 1-dimensional representation. This is 2-dimensional representation. It is obviously this is just mutual refraction. So they map the nu E into its antineutrino, nu mu into nu tau C, the anti-tau neutrino, nu tau into the mu antineutrino, and the prediction is very famous. You very well know. So C23 and RCP both maximum, but the maximal C23 seems disfavored by the present date. Present date favored the central value of present date seems larger than 45 degrees. It is in the second octet. And the minimal Fourier group we can produce in order to generate get a mutual refraction, we only need to start from D3. So it is a symmetry group or triangle. Very simple. This has been found by Ernest Ma in 1 year ago. Furthermore, we can get a general mutual refraction because the mutual refraction seems not favored, not so strongly favored by the current date. But Dean can also provide a scheme to provide an approach to fix this problem, the general mutual. And the radial symmetry is this one. The GL is a D-co subgroup. Dihedral subgroup is order 2-co. So these have to be have requirement on the N-co and the 2-dimensional representation. In the end, it equivalent from the symmetry point of view. It is equivalent to the D2 or K4. So it have to be RB. And X nu is Ry. Y is the power of how many times we rotation around the symmetry axis. Then we go back to the diagonal basis. Then we diagonalize the GL. Then we find it is still direct sum. It is block diagonal. But different first cases, they map mu1 neutrino into the mixture of anti-mu1 and anti-tau. Similarly for the tau neutrinos. So this is a general CP. If phi equal to pi over 4, we reduce to the refraction CP symmetry. And this is a prediction for the lepton mixing matrix. Use our master formulas. And we predict something. In this case, since the CP squares times sin 2 C3 squares is sin 2 phi squares. Phi is a discrete parameter determined by radial symmetry. And both Majorana faces is zeros. So if we want to get non-trivial general mutual reflection, that means no, it is not mutual reflection. The minimum group is D6. So this is the symmetry of six-sided polygons, and we can show the symmetry like this one. D2, it is abelian. It can fix the lambda mixing mixing in the time sector completely. And the prediction is this one. So you can see we gave the radical symmetry, we fix the relation between CP and C23. If we measure C23 precisely, we can determine the value of CP. This is a current bond, 3 sigma bond of CP. You can see it is very precise, almost fixed completely. For our D6, and we choose phi is pi over 6, it is possible value. By choose xy, by choose the index of radical symmetry, we can get the prediction for CP. And the mixed angles, the best value, fit value of mixed angles can be reproduced exactly. And the prediction for the CP phases is around 1.5 pi. Then we come to the second topic, to possible new physics, because this workshop is for new physics, quest for new physics. So besides the possible new physics or new symmetry in the Fourier mixing sector, we come to the possible new physics in the direct neutrinomous generations. And in Sang model, we start from effective field theory. The most general effective operator is this one. Its dimension is 4 plus 2n. So we can end h dag h n times h dag h. So this is the effective operator. Then we firstly go to the lowest level. N is 0. So d equal to 4. Dimension 4 renormalizable operators. There are tree-level contribution, it is well known, similar to the quark sector, and the one-loop relation discovered firstly by Ernest. But it's present for the tree level because tau mass is around the electroeccentric scales, but nu is order is mass of order EV. So there is a huge gap. So for the tree level cases, if we want to explain the tiny neutrino mass, at least some coupling, this one or the smaller one have to be tiny, or the mass of the particle in the loop have to be huge. So we want to discrete this problem, not so tight. Then we go to the next to NLO contribution. That we consider n equal to 1, the smallest one. So we follow the marching the diagram based approach. They have many. Then we find the topology for tree level. There are 4 independent topologies, and solid line is a formula. The dashed line is scalar. For one loop, we have 6 independent topologies. Then we assign the particle nu L, nu R, or H dagger to the external lines, and we solve by the inverse of gauge inverse, we fix the constant number of the magnetic fields. So for the tree liner coupling, it is Yukawa coupling, it have two Fermi fields and 1 scalars. This is the first one is SU2 invariant constraint. The second constraint is U1 invariant constraint. For the 4-point vertex, all the 4 points have to be scalars. They can involve 3 Higgs and 1 new scalar, or 2 Higgs, 2 new Higgs scalar, or 1 Higgs, 3 new scalars, and so on. And we can solve the constraint from gauge invariance similarly. So for each case, we can find many possible assignments. In the end, for the loop, we consider for the loop case, for the tree level it is very simple. But for the loop, we finally find 18 diagrams. It can fit in both the low order tree level diagram and the one loop D4 diagrams. And for each diagram, we have many possible assignments for the intermediate, for the massive particles. We only show the n up to 3. So there are so many possibilities. And this is prediction for the neutrino mass, and this is the constraint on the hypercharge if we want to exclude the low order contributions from tree level at the d equal 4 one loop contributions. And we as I have said, many different choices for the intermediate state. So Unix or the tree level UV condition is lost. Furthermore, similar to the Euro seesaw, we can use one stone to kill two birds. The two birds, first bird is neutrino mass, the second bird is dark matters. This is the ideal scatterogenic models proposed by Ernst. And to explain dark matter, the dark matter have to be chargeless, so this is how it poses constraint on the hypercharge at the ice spin of the dark matter multiplet. And the direction bound, we have to remove the tree level exchange, W exchange to scattering is nuclear. And the y-axis we have to equal 0. To guarantee the stability of dark matters, all the particles in the loop have to be old under a new Z2, dark matter Z2s, and other particles outside the loops, it is even. Then we can find the dark matter particles and its constraint on the hypercharge parameter alpha. So finally, the summary. In this talk, we first show after include CP symmetry, simple dihedral group is a good candidate for Fourier symmetries. We can explain the neutrino mixed angle, the CP phases, from smaller groups such as D3 or D6. Furthermore, this dihedral group can allow us to explain both quark and lepton mixing angles. Quark lepton mixing angle, the CP vector phases, in terms of 2 or few parameters. So it is prediction. And the minimal group is D7, 14 orders. Regarding the dynamic neutrino mass distribution, we perform a systematic classification for the NLO D equal 2 dynamic neutrino mass operators, and it's possible dark matter candidate. Thank you.
So, questions? Yes, please.
I have just a comment. I remember many years ago, people used D7
Yes.
to derive the Cabibbo angle.
To Cabibbo angle.
Yeah, but at that time, they obviously not do what you did.
Yes.
Because
No CP.
yeah, and
We cannot use CP values.
yeah, and so it was very complicated, and I just thought that that was not going to get anywhere, but you proved me wrong, of course. I mean, in those days, the model that actually allows you to use D7 to predict Cabibbo angle
Yes.
had to do a lot of other things to make the other numbers come out right,
Yes.
and rather arbitrary.
Yes. But this is fixed by symmetry.
Yeah, I know.
No arbitrary.
So this is good.
Yeah. Thank you.
Thank you.
So you're mixing of the DM part that's fixed by symmetry, the
Yes.
dihedral part.
Yes.
Do you have the actual Flavans? I'm just trying to understand whether you have a Lagrangian.
Yes. Yes. This is by symmetry. That means if we want to realize this symmetry, you have to add some flavors. It can also multiply Higgs to break the flavor symmetry, to break the original flavor symmetry to the radial symmetry.
So you have that explicit.
Yes, in a explained model, we have to include the flavors to break the
Right.
symmetry to the radial symmetry. But the prediction doesn't depend on how you break it. How by hand, spontaneous, or some other or tactical some others new idea. Nothing. Don't run it. Just fixed by symmetry. By symmetry breaking chains. Just by symmetry breaking chains. But in addition, I want to emphasize, given the radial symmetry, you can guide which flavors and its vacuum special value should be introduced. You can simplify the model building. This is model
I think
finite.
usually it's the other way because I think using this residual symmetry as a guideline with Lagrangian.
Yes.
Of course, you have all this nice prediction.
Yes.
But when you really do actual model building,
Yes. So it is simplified.
become a lot more complicated.
Maybe at present the model building
Predictions may get modified.
is complicated, but I think the dihedral group model building should be simpler than other groups with three-dimensional representation because dihedral group is very, very simple. I think this should be the simplest thing to model building because dihedral is too simple, right? Too simple. So the model building should be simple than other groups. This is second part I want to say. The group is simple, so model building is simple, right? You can just play 40 elements, and just this rotation or reflection. Not A4. A4 is three-dimensional. This is two-dimensional. Yeah. The first then is it can give the radial symmetry. It can guide which flavor fields and how what is this form or that which is the change. So it simplifies model building greatly.
Okay, maybe a last question.
Yes, I have a comment. Can you go back to page 7 or something? So I think this is always, I mean, this is at best an approximation, these residual symmetries. They're not really there, right?
Please, sorry.
I mean, these residual symmetries, they're not really there, which you have, they're at some approximation.
I agree with
I
you.
see these pictures all the time, but I mean, there are no such residual symmetries. You break the symmetry completely, you have, I mean, to some approximation, maybe at a normalizable level or something, you have the symmetry, but it's not really there, right? I mean,
Yes, I agree with you. At leading order, we
Yeah,
can
I
keep
know.
radial symmetry, but after including high-dimensional contributions from high-dimensional operator or the high-dimensional operator in the Taylor potential and others, it will break the radial symmetry, but it is high-order contribution. So the leading order prediction is preserved very well.
I agree with that, but I mean, there can be, yeah.
Yes.
You have additional,
You model the high-order contribution have to be under control, right?
Control break.
Yes.
Sure, but you have additional parameters, which are the coefficients of this high-dimensional operator.
This is general for any flavor models, I think.
Generic.
This is general for any model, I think.
Whenever you play forms.
Yeah.
They are
Okay.
always high-dimensional operators.
Sure.
You cannot avoid. Except you want to build a renormalizable model to introduce some message fields, okay, you face completely.
Okay, so this interesting discussion can follow afterwards in offline. Next time, next speaker. And the next speaker is Professor Anjan Giri, who is going to discuss leptogenesis in discrete flavor symmetry.
Good afternoon. I would like to thank the organizers for the kind invitation. I'll be talking about leptogenesis and in particular S3 symmetry, which is the simplest symmetry that we know. These topics are already discussed in the past, but I will see why I'm actually trying to see these things today. Baryon asymmetry of the universe is one of the problems that we have. Actually, it gives us an indication that there should be physics beyond the standard model, and there are already ideas that exist in the literature how to tackle them. And of course, leptogenesis is one such way one can actually explain the baryogenesis. And there are many studies with higher symmetry groups like F4, S4, etc. have been discussed in the literature as far as these kind of studies are concerned. But here we will try to focus, and all this we will focus on S3, and most of the discrete symmetries, including the lower groups, have been discussed this morning. And so I will try to see why we are studying today. And at the end, I will come to the conclusion. So far we have not seen any kind of indication physics beyond the standard model in almost all the sectors, be it the cosmic frontier, intensity frontier, or the energy frontier, except the fact that we have seen the neutrino oscillations, which actually gives us that neutrinos should be massive. But then there are ideas to generate this baryon asymmetry of the universe, which is one of the findings that we cannot explain. But there are ways to tackle that. So let's believe that this baryon asymmetry has been generated at some level, but presumably it cannot be before inflation. If it is so, then it will be diluted, or it cannot be after BBN, let's say after 1 MeV or so. So we believe that it should be somewhere in between the inflationary, after inflation is over, and maybe before the BBN, somewhere in this phase basically. And which we see actually today, it's at this temperature after 14 billion years. So we have all these very nice standard model where we actually explain the CKM mechanism, which explains the CP violation in the quark sector. Higgs mechanism gives mass to various particles, and standard model says that neutrino is massless, but the neutrino oscillation, as I pointed out, gives us indication that neutrino should be massive. And for that, the simplest thing that one can do is you add the right-handed neutrinos, and after you add the right-handed neutrino, you can explain many other things. So to explain the baryon asymmetry of the universe, we have the famous Sakharov conditions. We have to have the baryon number violation, C and CP violation, and out of equilibrium. So these are the three conditions required to generate the baryon asymmetry of the universe. And we are very sure that there must be physics beyond the standard model, because most of the results have explained whatever we see today, but there are dark matter, BAU, baryon asymmetry of the universe, etc., etc. So these are the findings that actually lead us to believe that there should be physics beyond the standard model. At the same time, the standard model should be a low energy effective of the new theory that we are actually looking for. So here in this context, we know if you want to explain the baryon asymmetry of the universe, the moment you introduce the right-handed neutrinos, then you can actually use the famous thermal leptogenesis, where you generate the lepton asymmetry, which can be translated to the baryon asymmetry by the Spelleron processes, and one can account for this kind of observation. So I will make a digression here, because what we have learned so far is that we have been using various symmetries to find some experimental data, but here I will use some bottom-up approach. We have not seen any indication of physics beyond the standard model, but there are some indications in the flavor sector. We have learnt yesterday that there are some problem in P prime, particularly RK star, which are the quark level transitions in B going to S decays basically. And that was expected for quite some time that if at all there will be new physics, then in the flavor sector they should show up in B to S transitions, which I think there is also another problem called the lepton universality problem, which is I think it's a problem really, we don't know. But there are various models people have actually proposed to explain this kind of models, this kind of observations. So one such observation in the flavor sector, which is called RD star puzzle. So what it says, this is an observable RD, which is the branching ratio of B bar going to D plus tau minus nu, and taken the ratio of branching ratio of B minus going to D plus L nu, where this L is not tau. So that means this is either electron, these are combinedly electron and muon, and that is what is called RD star, the observable that we define here. Similarly, we have in the vector mode RD star, which is B bar going to D star plus tau nu tau, and it is divided by B bar going to D star plus L nu L. Again, here in this case also, you can see that this lepton corresponds to muon and electrons. So somehow, if you look at the experimental values, of course, these puzzles are there for last few years, starting from 2012 onwards. We have been seeing these observations. There is no clear indication. We can see that this is something like 4.1 sigma deviation from the standard model expectation. So what we get basically from the various observables that we get from Bell and Babar and LSCB, that you have this RD, the experimental value is something like 0.47 plus minus 0.039 and plus minus 0.024. Similarly, for the RD star, the other variable, you can see that the value is 0.304 plus minus 0.013, etc. Now, if you look at the standard model calculation for these two variables or the observables, you see that RD star is simply 0.298 plus minus 0.003. So the error bar is quite small here already, theoretical error. And similarly, you can also have RD star, it's a standard model which is simply 0.255 plus minus 0.004. And to validate this, we have these lattice calculations, and where you can also see that this RD standard model is quite similar to what you see here, and RD, this is should be RD star. Okay, sorry, these are the two by the different lattice communities, and so we see that there is some kind of deviation here, and the deviation is not coming down. It is actually, if you look at this plot, the left hand side it is RD star, and right hand side it in the x axis it is RD, and this one basically, this one is the standard model with very less error bars, and you have the results from Bell, and then this is from Babar, and this is from LSCB, and some independent measurements by Bell. So what you can see that the combined average is somewhere here, and the standard model is very much away from this one, namely 4 sigma. Now what we believe, the Bell is going to start in couple of months from now, and LSCB is continuing to give us more and more results in this sector. But what we believe, once Bell starts, then this error bar will certainly come down. And let's assume a scenario in which so the systematic uncertainties go down, then you have, and your central value still remains around this point. Then maybe we will see, apart from the lepton number universality violation, this is one such observable in the flavor sector which may give us some indication of physics beyond the standard model. Now at this point, there have been many models proposed in the literature to explain this kind of deviation, and mostly the familiar ones are Z prime, which is while you introduce a U1 group, or the leptoquarks. Okay. So we don't know how it will be basically, whether this central value of experimental variable will approach the standard value or not, that we don't know, but assume that this stabilizes around this current central value, then we have really a problem in the flavor sector. Now let me go back again to the slide just to remind you that if it is a problem, then you can see that what it says, it's RD, where you have the third lepton tau namely, and the other one is combined in the other group, that is muon and electron. Similarly in the RD star also the same thing, you have the third lepton and the other two lepton. Is it giving us something new, some clue for the physics beyond the standard model? And that is what I wanted to explore here. So the simplest group that one can think of in the flavor geometry is the S3 group. So what it says, So you have only one doublet representation and two singlet representations. This has already covered by the previous speakers. So you have these properties for the group elements, and you have, I don't want to repeat those things already discussed, but the point is that you want to have one doublet and then singlet representation, which actually we'll use here. So before we go to explain S3, also we also know that the electron mass, the lepton mass is found to be very small, and there is already a hierarchy. And as we know that in standard model, right-handed neutrinos are not there. So if you introduce right-handed neutrino to give mass to the neutrinos, then eventually one can actually use the famous seesaw mechanism to explain the smallness of the neutrino mass. Or also, the moment you have the right-handed neutrinos, they can also give us some kind of a complementary picture that quarks and leptons are of the same kind, because you don't have right-handed neutrino in the standard model. Once you introduce the right-handed neutrino, it will be more or less complete. And so also we can also explain the leptogenesis with the help of the standard type 1 seesaw, which is very famous. But to name, I think it is very well known that there are three kinds of seesaw mechanism. For the first one, type 1, which is actually introducing right-handed neutrinos. And then you have type 2, which is by introducing some new particle scalar triplets. And then type 3 is basically the fermion triplets. So in this model, what we'll do, as I said, that it's a very simple model. So what we'll do, we'll actually consider this kind of particle contents. So we'll assign the first two leptons, doublets, L1 and L2, in one S3 doublet, and the third lepton, this is dictated by what I saw in the previous experiment, that somehow the muon and electrons, they are behaving in a different way in comparison to the tau sector. So now the L3 sector, the tau sector is now separated from this picture, and I have the corresponding right-handed sector, right-handed neutrino. So I have introduced three right-handed neutrinos, and similarly in the Higgs sector also we have three Higgs we have introduced, and additional two scalar triplets. So you can see that these are the triplets, and corresponding hypercharge is given here, the S3 quantum number, and correspondingly I have also introduced the Z2 symmetry. So what I will do, I will try to see if we can explain successfully the leptogenesis using the scalar triplet. Remember, since my symmetry is S3, so my parameter space is very much limited. So one can write using the two triplets, scalar triplets, the corresponding Lagrangian, which is very well known. I am not going to go into the details. So once you write these things, so what you see that the flavor structure is very much diagonal. But at the same time, when I introduce this scalar triplet, my objective is also to explain the neutrino phenomenology. Otherwise, it doesn't make sense. So what I'll do, because this mass matrix is diagonal, so I have to introduce some right-handed neutrino. So that means instead of just only type 2 kind of seesaw scenario, I will also introduce the type 1 seesaw. So now this scenario is actually a combination of type 1 and type 2, or you can say the hybrid kind of seesaw. So once I introduce the right-handed neutrinos, including the S3 symmetry, I have the corresponding terms which are coming from the right-handed sector, and these are the corresponding Yukawa couplings, etc., etc. And then I will try to see the mass matrix is the famous type 1 seesaw formula. One can find out the neutrino mass matrix since I have already the right-handed neutrinos. Because of the S3 symmetry, my mass matrices are Dirac type and charge lepton matrices are like that. And you have the corresponding definitions that I have used, whether these are the Yukawa couplings. Since I have introduced three Higgs doublets, so then my doublet potential looks something like this, which is, and also since we have 3 doublets, so what I'll do, I'll redefine the doublets in terms of H1, H2, or in terms of H1 and H2 in terms of H plus and H minus, and H3 is kept as a separate doublet. And I can introduce some kind of mixing, which is basically wave of V plus and V3. And this is required because it will be clear soon, because I want to have some kind of a different Higgs other than the Higgs, other than the standard standard model Higgs, which should be very heavy. Otherwise, it will actually give me efficiency decay. So similarly, the scalar triplet, because of the 2 scalar triplets introduce potential like this, and the total potential, scalar potential will be VD and VAT. And I will use stabilized conditions to find out the stability in this sector, which is not mentioned here. Now, if you look at the charge lepton mass matrix, as I pointed out earlier, from the type 2 sector, I get a very diagonal structure. So that's what I introduce the right-handed neutrinos to make it to make it non-diagonal, and I will try to explain the neutrino phenomenology. So the combined mass matrix looks like this. And one can redefine this in terms of various observable, so that my mass matrix is like this, is a combined type 1 plus type 2, where phi effective is some remnant phase. So since I am using S3 symmetry, I can rotate this in terms of some one of the S23 operator, so that it becomes block diagonal, and I can actually use this, I can diagonalize 2 cross 2 matrix to get some values, and this can be actually compared with the UL dagger U nu, and I can compare with the elements of PMNS matrix, and I can successfully explain the parameters that we find from the neutrino sector. Coming to the leptogenesis, these are again standard formulas. What I have done, this is the right-handed neutrino going to LH, and you have the lepton asymmetry. But instead of type 1 symmetry, type 1 CISO only, I have also type 2. So I have scalar triplet. They will also contribute to the loop and vortex diagrams. Since I have 2 types of type 1 and type 2 contributions, so we have actually 3 scenarios in which we can have either the leptogenesis coming from right-handed neutrino, which is pretty standard. So I will start with the leptogenesis coming from the scalar triplet. Now we will use the out of equilibrium decay of the scalar triplet. So we will assume that one of the triplet is smaller than one of the triplet is smaller than the other triplet, and also the right-handed neutrinos, and then they will contribute to the lepton asymmetry, because so you have the lightest particle contributing to the leptogenesis, and so the condition is that when the mass, the temperature will be less than mass of the particle, so that will be out of equilibrium, which is pretty standard. And then I can find out the corresponding lepton asymmetry epsilon data using the previous formula, and these are some definitions. Corresponding asymmetry from scalar and from Higgs and from the right-handed neutrinos. I will combine all these contributions from various right-handed neutrino sector and scalar sector to see whether I can explain the lepton asymmetry. So similarly, in the case 2 case, what will happen? I will have a scenario in which let's say the scalar triplet mass and the right-handed mass are almost the similar size. So then that one can actually use some kind of approximation here, and then here also I can see that there will be contribution from both scalar sector and from the right-handed sector. And the third case could be the simplest one, which is the right-handed neutrino, which I don't discuss because it is already there. So one can actually use the Boltzmann equation to find out the efficiency factor, and all the technology that we know in case of leptogenesis will be used, and one can see that these are the so the one of the important things in leptogenesis is to see how low it could be, the mass of the let's say right-handed neutrino. This is basically taken into this plot is basically mass of the right-handed neutrino versus the epsilon Cp that we know today. And we can see that if it is greater than say 10 to the power 10 GB, then maybe we can explain the observed Cp asymmetry. Similarly, this one is basically only for the right-handed neutrinos, and left-hand side is plotted the y Cp, and this is plotted about Z, which is mass over temperature. So one can see various contributions that I have mentioned earlier, and one can actually explain the observed Cp violation in the leptonic sector. And this one, if you introduce both, if you actually include both right-handed neutrino and scalar triplet, we can see that the lepton asymmetry is actually enhanced. So, to conclude, we have used some data in the flavor sector, namely the RD star puzzle in the quark sector, to see that whether S3 kind of symmetry, which is very simple, can actually connect both the observation in the neutrino sector and also explain the leptogenesis. The question is whether there is any connection. Maybe yes, maybe the actual symmetry is very much complicated, but maybe we have exciting time ahead, and maybe future results can give us more clarity. And thank you very much.
Thank you. Any questions, comments?
Yes, please.
Yes, please, Evelyn.
So you surely mentioned this, but I missed it. So why do you need two different scalar triplets, delta 1 and delta 2?
Oh, okay. So that is because if you have, I think it is already proved in the literature, if you have only one scalar triplet, then it will give, then you have to go to 3 loop to generate the lepton asymmetry, which will be very much smaller. So in order to have in the one loop, we must have at least more than one scalar triplet. Okay. So that is how it is to introduce.
Even if you have right-handed neutrinos?
Yes.
Okay.
Yes.
Other question? Well, if not, then let's thank the speaker again. And our last talk for this session is going to be given by Dr. Julia Haas on a global fit of right-handed neutrinos with gambit.